I'm here to demonstrate accelerating S3 data lakes using FSx for Lustre. So in my demonstration today, I'll be creating an FSx for Lustre file system linked to an S3 bucket. This S3 bucket is the S3 data lake. This environment will be accessible from an AWS parallel cluster as well. So to create the file system from the FSx console, I click Create File System. A typical network shared file system is a scale-up file system, meaning that the file system is hosted on a single node. To improve the performance, you need to scale up the resources like network, CPU, disk, memory on that server, but it's still a single node. Lustre is a scale-out or parallel file system, meaning that there are multiple file servers hosting the file system. In order to get better performance, you add additional file servers, and the Lustre client can access all these file servers in parallel. So today with my file system, I'm going to give it a name called Pi Day Demo, of course, and it is a persistent to SSD file system. It will have an 86.4 terabyte storage capacity. And if you look at the throughput capacity at the bottom, you'll see it change as I select the different throughput per unit of storage options. I'll be creating 1,000 megabyte per second per terabyte file system today. Lustre linearly grows. So as you add additional storage capacity, the throughput also grows linearly. I select the VPC, the network security groups, and the subnet for where the file system will reside. And I'm going to link it to my S3 data lake. The data lake will actually be mounted as the root of my file system. And I'm going to be linking it to my US West to NASA NEX S3 bucket. The import policies are configured so that when changes are made to the S3 bucket, they are reflected in the file system, and the export policies, any changes to the file system, are reflected in the S3 bucket. So now when I'm ready, I can create the file system. For the sake of time, I sped up the video, and within just a few minutes, the status of the file system will change from creating to available. I want to dive deeper into the file system itself, so I click on the file system ID. And I really want to look into the data repository that I created, so I click on the data repository task. The time it takes for the data repository to get created really depends on the number of objects in the S3 bucket, as well as the storage capacity of the file system. So in a few minutes, the status changes from creating to available. All the nodes of my parallel cluster have the file system mounted as /FSx. But I want to dive a little deeper and take a look at some of the details of my Lustre file system. So I execute a Lustre disk free command. As you can see, there are a lot of different OSTs, and there's actually one MDT at the very top. An OST is an object storage target, and an MDT is a metadata target. You can think of object storage targets as the disk storage, similar to what you see here in this diagram. And two of those object storage targets are attached to each file server, and in Lustre terms, those are called object storage servers, or OSSs. So this file system has 72 OSTs and 36 OSSs. I want to do a quick ls against the file system, take a look at all the directories under the root of my file system. And those correspond with the prefixes in my S3 bucket. So my first test, I'm going to be creating I'm going to be accessing a small data set. It's about 57 gigabytes in size, 48 files. And what I want to do is basically download those objects from S3 to the local storage of my parallel cluster. So I'm not using FSx right now. I'm just copying it from S3 down to the local storage of these compute clusters. So I execute my sbatch command. I take a look at the queue, and I see that all 16 jobs are running. For the sake of time, I sped up the video, and now I'm going to look at the output to see how long that took. So each compute node took about 6 minutes, 35 seconds in order to download from S3 to the EBS volumes on those. Now that the data is loaded, I want to go ahead and read the files from the local EBS volumes on my compute nodes. I execute an sbatch script again. And after a few minutes, I speed up the video. And after a few minutes, the read is completed. I can take a look at the output. So it took about 7 minutes, 10 seconds for all of these instances to read that data. Now I'm going to accelerate. This was about 13 minutes, 45 seconds. Now I'm going to go ahead and accelerate that using FSX for Lustre. I'm going to tell FSX for Lustre to go ahead or the compute nodes to read all the data from the Lustre file system. So the data doesn't exist yet, so it's going to go out to S3, get that data, store it in FSX for Lustre, and then deliver it to the clients. I sped up the video, and we could take a look at the output. So it only took 15 seconds for this to happen using FSX for Lustre. So much faster than using the old method that we used to use when we just copied data from S3 over to the local storage. We can see that the 48 files have an exist archive status within Lustre, meaning that the data now resides in the file system. And we can see that all the OSTs have some type of data of my data set being stored in the file system. Now that the data set is done and my job is done, I can actually release the data portion of all of these files. I'm going to go ahead and keep the metadata, but I'm going to release the data portion of the files. So a simple HSM release command is executed just in a few seconds, and you can see that the 48 files now have a released status. If we take a look at the Lustre disk free command, we can see that all of that space has been freed up. So my next test is going to be much larger. I actually have a data set that is 9.6 terabytes in size. It's made up of a lot of net CFD files, as well as some MD5 hash files. I can do a simple S3 LS against the linked S3 bucket and take a look at all the different objects that are sitting out there. Now, these objects, the data portion of these objects, don't reside in the file system yet. I'm only really worried about the .nc files or the net CFD files. I'm going to go ahead and just run a quick LS against that, and I see that it's still 9.6 terabytes, but it's 7,134 files. I'm going to issue a command now to Lustre, basically telling it to preload these 7,134 files. After just a few seconds, it's going to go ahead and load that data, or execute the restore command. And if we hop over to the CloudWatch metrics for my file system, I can see the performance the file system was able to achieve. So again, I sped up the video, and after about 3 minutes, we see that we were able to achieve 88 gigabytes per second of throughput, downloading that 9.6 terabytes to the FSX for Lustre file system. We can see that those 7,134 files have an exists status, and we see the data is spread evenly over all of the OSTs in the file system. Now, what I'm going to do is execute basically a read command against my parallel cluster, telling it to read all of the data, all 9.6 terabytes from each node. For the sake of time, I'm speeding up the video so that we can see that we're able to achieve very high levels of throughput during this read operation. We were able to achieve just under 99 gigabytes per second of throughput and averaged around 97 gigabytes per second of throughput during this job. We can see that all of my compute nodes had very high levels of network in traffic. Now that the job is done, I can take a look at the output to see how long it took. And we can see that it took each node approximately 30 to 33 minutes to read all 9.6 terabytes of data. Typically, after a job, you want to create some log files or some output files. So I'm simulating this using small file. So I'm going to create 1,064K files, and I'm going to write it to the FSX file system. So it's going to be in the output directory. If I do a simple list against the root of my file system, I can see the output directory there. If I hop over to the S3 console and do a refresh, I can see that now that output directory or prefix is now in my bucket. And if I go into all the different prefixes, I can actually see those files have now been exported to my S3 data lake in my S3 bucket. Now that the data has been processed and read for my job, I can go ahead and release that. What this will do is actually free up the space on the file system for other jobs to run. My output files have also been written to S3, so I can easily release them as well, freeing up even more space. So after just a few seconds, all of the data that I just processed and created has been released from the file system. And if I run a simple Lustre disk-free command, I can see that all the space has been freed up. So this was one example of accelerating S3 data lakes using FSx for Lustre.
Awesome. Well, thanks so much, Daryl. It's really remarkable to see how much it truly accelerates S3 data lakes. A follow-up question. What are data repository associations, and how does FSx for Lustre use them to link to S3?
Yeah, so data repository associations, or DRAs, is a way that we can link an S3 bucket or prefix to a specific folder or directory within FSx for Lustre file system. You can have up to 8 DRAs associated with the file system, and each DRA can have its own import and export policies associated with it.
Awesome.
Thanks, Daryl.
Great.
We always enjoy a good demo.